Okay, welcome everybody to our series of webinars where we'll be showing the main capabilities of Civil Fan. Okay, this webinar is organized by CAE Solutions. It's prepared by, as you can see in the slide, by Engineer Aneris Hernandez. As it's presented by me, Engineer Luis Lozada. Okay, we are part of the team of CEA Solutions. Okay, well, let's start by telling you briefly who are we. Okay, CEA Solution is Indie Cyber partner, as you can see in the slide. We are distributors of Civil Fan in USA and Latin America, and we also provide specialized solutions, in computer aided engineering. We have a company. Our company is registered in Florida, and well, we have a team that is composed for people with more than 30 years of experience uh, in the professional area. And well, we give a service of quality in order to increase the productivity of our customers. For all of us, it's always very important getting to know the basics of all the softwares and the tools that we use in our profession. Okay, so therefore we have to know, and we want to explain basically what is Civil Fan. Okay, and this is a technology that is powered by Mark. Okay, it's a structural software that we call everything in one. Okay, it combines the use of modern graphical environment and for analysis tools for professionals and academic user. Okay, in this software we can solve and we can evaluate problems with high nonlinearities, transient analysis, and staged construction process uh, in a great manner. As you can see here in the slide, we can evaluate soils, dams, steel structures, bridges, and as I said before, everything is in only one software. Okay, I would like to explain some features of Civil Fan. Uh, we have a very graphical user interface, very friendly. We can develop scripts with Maker's Python, and we have an automatic analysis report, and everything, as I said, is located is developed in only one software. In the structural analysis, we can evaluate, linear and nonlinear static analysis, trenching analysis, nonlinear buckling, model spectrum analysis, harmonic analysis. In concrete, we can evaluate creep, shrinkage, advanced material behavior, and cracking propagation, heat transfers, and all of those topics and behaviors that have high nonlinearities. Well, in this time, in this example, we're going to develop a shear wall. We're going to evaluate a shear wall, okay, that is coming from detailed advanced concrete analysis, where we're going to apply cracking behavior to a segment between two floors as I said, of a shear wall with different reinforcement configurations. So as you can see here in the image, this is to the right, this is one of the shear wall, and we're also going to evaluate the behavior of such shear wall uh, with an opening, in the middle point of the shear wall. Here you can see in the image that this is the portion that we're going to evaluate, and you can see in these images that We also have the geometric definition of the behavior that we're going to evaluate. Basically, in the first image, we have a distributed uniform reinforcement each way. Okay, then we have the same reinforcement with a diagonal reinforcing added, and we also are going to evaluate the shear wall, the portion of the shear wall with an opening inside. So we consider two types of concrete according to the ACI 318. Okay, we have one concrete for beams, okay, with linear behavior, and we also have another for the wall, where we're going to take into consideration the cracking properties. For example, we're going to have a maximum tension stress for cracking as 0, no tension stress allowed, and we're going to have a shear retention factor, okay, for taking into consideration the reduction of the shear stiffness around 50%. Okay, so now we are going to evaluate this model using the software, and well, I'm gonna take you through the modeling process. So in order for you to evaluate, and observe the such modeling process. Okay, I'm going to open the software. Okay, and we are going to start by evaluating the shear wall as a solid shear wall without any opening and with a regular and uniform distribution. Okay, I'm going to start to shear. Okay, so here you can see the shear wall geometry. Okay, I'm going to rotate. As you can see here, it's very easily taking the view of our models, so you can rotate in an easy manner with by the axis, and and you can evaluate the perspective that you would like to see when when you develop your models. Okay, now we're gonna go through the geometry tab, where civil fan we have a different alternative for modeling, such as lines, axes, polylines, circumference, and they are inside of the three main characteristics. As curves, we have surfaces, volumes, and operations. That's okay. In the surfaces, we can see the triangles, the quadrilateral. We have primitive. Okay, and we have different alternatives for making the modeling process. Okay, when we go to the model tab, we have two main sections, which are materials and cross sections. In materials, we define the properties such as steel, concrete, reinforcing steel. We also have the capability of evaluating rocks, soils. Okay, and we can define generic materials. Okay, and in the section, we can define whatever section we're going to model to our element. We have such as the library from codes, from different codes. We have concrete sections. As you can see here, we have cables sections, and concrete sections, and we also have generic properties for those sections. Okay, once we define our materials, we can see here in the geometry that on civil FEM we have a group where we can see the entities, the entities characteristics such as line, point, and once we click on that element, we can see the property which defines that element, that geometric element. Okay, uh, here in the entities dialog box, we have the F prime C for the concrete, that in this case we define 4,000 psi for the concrete and 60,000 psi for the reinforcement bars. Okay, so as you can see here in the properties dialog box, we have the normal properties such as Poisson modulus, we have the modulus of elasticity, uh, we can define the edges of the concrete, we have the capability of evaluate our analysis with different edges on concrete. We also have the capability of make cracking analysis. Okay, so in this case, for the shear walls, we have defined that we're going to take into consideration the cracking propagation for the shear wall. So we also define that the shear retention, which is the shear stiffness loss for the shear wall, is around the 50%. Okay, as you can see here, we also have we can define the behavior of the concrete. Okay, so for different edges, and a great powerful characteristics for this software is that you can modify and you can define your own curve for the concrete and your own model. Okay, in this case, we can see that this is the Hognestad model, this parabolic rectangular diagram, and we have the curves for all the edges, in our on the. Okay, we also can define, long-term characteristics such as creep and shrinkage, and we can define for dynamic analysis the damping and all the characteristics for such evaluation. So that's basically what define the material properties, okay, in this property window. Okay, in this case, now once we have defined the material properties and we have defined the sections, we go to the mesh tab where we assigned the structural element. Here you can see that we have three main characteristics here. We have the structural element where we have beam, trusses, shell, solids, and cables. In this example, we assigned a shell structural element for this example. Okay, and we have the model units where we can assign the connection properties, the mass, insertion, springs, and all of that. Okay, so there is a very important characteristic here because, for example, we can make a question and you can ask, okay, how can we make the bonding behavior between the reinforcing steel and the concrete? Okay, so the main capability of civil FEM is that we only have to make a few clicks. Okay, we only have to make a few clicks and define the bonding characteristics between two elements. In this case, we have the concrete elements or the shear elements and the bars. To the right, you can see that we have the insertion point. Okay, in this case, we take a host element that in this case is the wall. Okay, and you know we have the inserted elements, which are the bars. Okay, so in this software, it automatically make a routine where they can simulate the bonding between the bars and the concrete. Okay, so in the same way, we can evaluate the non-linear behavior of contact. Okay, if we go to the mesh tab, here you can see the reinforcement, how it's defined graphically. Okay, so we have the capability to model. In this case, we're not using this. Okay, but we have the capability of the evaluate the contact between the elements. Okay, you only have to select one main element and one secondary element. Okay, and you're going to model the different types of contact. Okay, we have to evaluate the glue contact and among others. Okay, so basically, instead of have difficult and very long routines, here in Civil Fan, you define the geometric elements and you make the meshing, and also the mesh is done automatically by the program. Okay, the program and the routine is in charge to match the nodes, to match the elements, and they're making the proper line and surface constraints, for getting the bonding behavior, and that is made automatically. Okay, so when we have defined the structural elements and we have defined the connections, the elements inserted, the contact, now we're going to define the loads. Okay, in this case, okay, defining a lateral displacement. Okay, you can see here, let me mark here, and displacements are defined as a boundary conditions. Okay, so I'm going to loads and load case. Okay, I'm gonna select the load case generated. Okay, I'm going to show a lateral view. Let me check here. Okay, so in the top right corner, you can see the graphical representation of the displacement. Okay, and we also can see the boundary conditions then that are applied in a very easy way, because you only have to select the line and you have to select the element, and in this case, for example, we have two beams in top and bottom, and we applied different conditions for the boundary conditions. Okay, we only have to select the line, and the routine automatically assign a linear support to the beams. We don't have to go node by node. The program automatically recognizes that all the meshing nodes that conform the two elements that are inserted and in contacted, and it applies the boundary conditions automatically. Okay, as you can see here. Okay, so once we have defined, it could be the load, it could be the displacement, and we only have to solve the model. Okay, we have a very powerful solver, and where we can evaluate high nonlinearities, okay, large deformation, we can evaluate friction depending on the kind of contact what we have defined, and we can evaluate long-term properties, talking in concrete, and you know all the nonlinearities are captured automatically because they have been defined by parameters. Okay, so we define the parameters, and starting from that point, the program automatically capture the nonlinearity. Okay, and it's a very powerful tool and easy tool, to handle. Once we have the result, I'm going to show you. In this case, we're going to evaluate the crack propagation. Okay, we load the file, and we're going to see the cracking strain. We're going to see the cracking strain in X direction. Okay, we just plot the information. Okay, so I'm going to show you the front view of the model. So basically, you can see here the spread of the cracking deformation in the wall. And we also can see here that in this case, the acceleration is the separation of the particle that it's going to happen vertically, okay? Because the x axis is going upward, okay? So we can see that the vertical the vertical strain, okay, there is governing the condition is in the top and bottom extremes, opposite extremes, in the left bottom corner and the top right corner. So you can see the spread of the cracking, observing the minimum values in the blue area, and it's going, it maintains the contour in the yellow area, but the streams and the higher values is located once we make the displacement at the top and bottom right opposed corners. Okay, so I would like to show you the cracking strain in the XY direction, or the XY component. Here you can see that in this case, this is the in-plane shear that is happening product of the displacement, and in this case we can see how the program can capture the nonlinearity of cracking analysis, and it shows us how is the spread of the cracking once the displacement is applied, you know and well, in an easy manner, we can use this software. Due to the high nonlinearity performance, we can use the software for calibrating real models, for making investigations, and for forensic engineering is a powerful tool, because automatically and very quickly we can evaluate this complex behavior. you know there is an concrete cracking, and taking into consideration the bonding of the steel, the interaction of the bars, you know and all of that means for the cracking analysis. Okay, so now I would like to show you another model that we developed, okay, where in this model we have the shear wall, okay, but we added, as I said in the slides, two diagonal bars, two diagonal reinforcing bars. Okay, now we are going to see here, in a very easy way, we can define the bars, we can define the contact and all the process that I said, I'm just adding the bars. And now we're going to evaluate the results, how now the cracking is spread. Let me check here. Let me open. Okay, and so we also, let me find here the X direction component. Okay, so now we can see how the magnitude of the strain, although the strain is distributed in the same manner in the central part, but you can see here that the magnitude of the strain is less in the center compared to the previous model. So, and you can see that how the zones that are located, that are bounded between the diagonals and the corners, okay, are high stress also. Okay, so now I would like to show you the Y component of the strain, cracking strain. In this case, the strain, the strain which is located, and first of all, I would like to tell you that, the X direction of the shell element in this case is going horizontally. So you can see how the crack, there is the separation of the particles that are going in Y direction horizontally. You can see where they are located. Okay, now I'm going to show you the XY component of cracking strain. Oh, sorry, this is not is. Let me check here. XY, that's right. Okay. 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 As you can see, how we can capture the spread with the new configuration of the bars. Okay. So now I'm gonna show you that we develop a model with an opening inside. Okay, let me open. Okay, in this point, we develop a model now applying an incremental load. The model that we saw before is is this same model, but with a displacement. Now, as you can see here in the properties, we're going in the conditions, we applied a load, okay, and let me check something here. This is not a model. Let me get the model, the proper model, please. This is the OP. That's right. Okay. Okay. Let me get. Sorry for that. This was the same model. So I'm going to show you, the geometry and the load case. Okay. So this time we applied an incremental load, a lateral incremental load, and the main point here is that we wanted to evaluate the spread of the cracking step by step, making a non-linear step-by-step analysis. So here you can see you only have to define the solution control, uh, the steps, the intervals, the tolerance, okay, the convergence factors, and you only have to run. And let's see the information, the results. Okay, okay, so let's load the information in the first step. Okay, we're going to evaluate the the Y strain cracking component in this case. Okay, there is no a big effect. Is everything going very very plain? So now we're going to evaluate the XY component of cracking strain. Okay, so in this first step, okay, you can see that where the propagation of cracking begins. You can see here in this corner, and we're going advancing step by step, and you can see how the magnitude is increasing, and we can see how the spread of the cracking for this shear wall. Okay, we're going to this step. So now you can see the order of the magnitude. We're going at 0.14 as a strain, 0.16. Okay, so basically, if you go further, you can make an analysis where you can take the structure as you were doing a pushover analysis, where you can evaluate the cracking, then you can evaluate the yielding of the steel, and once we get to that point, that well, we didn't do that here, but when we get to that point, we can evaluate the plastic equivalent deformation of the bars. We have the capability. Okay, so we have different models for capturing the plasticity and evaluation of the thermal mechanics of the continuum. Okay, so in this case, we only push the structure. In this case, we only push the structure until getting the cracked behavior, but we could go further and having a more complex behavior. So basically, as I said, this is a great capability for forensic engineering, and for structural assessment, and all of those problems that we have daily in the engineering field. Okay, now I would like to show you the model that we developed, taking a opening in the middle of the shear wall. Okay, as you can see here, I'm going to show you the reinforcement. Okay, we added these diagonal bars for having the shear concentrations on the corners of the opening. And well, now we're going to see how we can capture the behavior for cracking here with civil fan. Let me check here. Okay. Okay, let's find the cracking strain, the X component of cracking strain in this case. So you can see it's important to notice that the X component of cracking strain, if the deformation or the separation of particles which are going vertically. So once we know that the separation, the kinematics of the particle is going vertically, the spread, and the pattern it's going horizontally. Okay, so we can see here in this point. Okay, I'm gonna show you here, for example, if we have a crack pattern, okay, and we have 2 points or 2 particles, and this is the deformation. We have the rupture of these 2 particles. Okay, they're going in upward direction, but the pattern which is created is going horizontally. That's that we are trying to represent here with the software. So the maximum amount of this pattern or this cracking strain, as you can see here, are in the corners because we have high stress concentrations and cracking on that point. Okay, so let's see now the XY component of cracking strain. Okay, now as you can see here, the XY component, is like the plane shear, which is going in the particle, and as we have a reinforcement in in the 4 corners of the opening, the most stressed part of the shear wall now it's going to have place to a side where we only have a regularly or a uniform spaced vertical bars, okay, which are basically working for taking the tensile forces product of the couple, okay. We have a with a very short height, okay. We know that the shear deformation is gonna govern over the bend and deformations. So now we have here what would be the cracking, and which are those zones where we have to pay attention when we're going to make the proper reinforcement. Okay, now I would like to show you this same model without the diagonal bars reinforcing in the corners. Let me open here. Okay, as you can see here, I'm gonna hide the shell element. This is a regularly spaced reinforcement bars, and we don't have those diagonal bars for protecting from the high concentration of stresses in the corners, the shear stresses. And well, I would like to show you what happened when we applied such displacement, lateral displacement. Okay, I'm gonna show you the XY cracking extreme component. Okay, now you can see here the behavior. A time before in the previous model, we can see here that this kind of behavior were concentrated in the 2 middle parts, each side of the opening. Now we can see how they spread. Can you see this yellow part, which is going in the right bottom corner? So that means that, the cracking propagation, it's going, because, when we get cracking in a point, we're going redistribution of the stresses, and, the stress, it's going where it can deform, where it can, crack. And from that highest stress point, they moved to the corners where we have, a high concentration of this kind of stress. But, as I said, this is a very easy way of evaluating our structures, and, trying to catch the real behavior for, for optimizing, and, our design process, our this decision making, when we're going to make any assessment, or we're going to make uh, any reinforcement. So, as I said, these are the models that I showed you. Okay, and as I told you, these were the characteristics for getting the insertion point, the insertion of bars into the concrete. Okay, these are the, as a summary, these are the boundary conditions we basically used. Let me go to the next slide. And here we have a summary of the behaviors that we evaluated. Okay, so you have here the summary that we've been talking through this webinar. So basically, I can conclude that, we have a powerful tool, and is a very easy to use, and, well, we can capture in an easy way, a very easily manner, all the complex nonlinearity of the structures. Okay, so I don't have nothing more to say. That thank you for your time. Okay, for sharing with us. I know that, this is a very important effort that we all make, and, and you are the important point here in this webinar. I hope you have enjoyed, and, well, I just want to say that every Monday, and, at 8 in the night, we make these webinars where we discuss a little bit different topics, different real situations that we have evaluated, and, well, it's maybe a good moment for, for sharing engineering. So thank you very much for your attention. Okay, if you have any question, any clarifications, please do not hesitate in telling us by the chat, or where, or contacting us by mail. Okay, thank you very much for your time.